Okay, problem 3.11 is asking us two things. First, find the momentum space wave function phi of p comma t for a particle in the ground state of the harmonic oscillator. And then part two, what is the probability that a measurement of p on a particle in this state yields a value outside of the classical range for that same energy. So let's look at this in steps. Step one, find the momentum space wave. Find the momentum space wave function. That is effectively just asking us to plug into the Plancherel theorem and convert our position space wave function into a momentum space wave function via the use of a Fourier transform. So let's do that first. That's technically sort of the easy one, right? So we know that the ground state wave function for the harmonic oscillator from back in chapter 2 is equal to psi naught equals, and just to emphasize everything, it's psi naught in terms of x comma t. This is equal to the constant m omega over pi h bar to the power of 1/4. And this is multiplied by e to the power of negative m omega over 2h bar multiplied by x squared. And then this is multiplied again by e to the negative I omega t divided by half, where this is sort of our time-dependent form with our energy. So if we want to find the momentum space wave function, we just plug this into Plancherel's theorem, recognize that phi of p comma t is equal to 1 divided by the square root of 2 pi h bar times the integral from negative infinity to positive infinity of e to the power of negative I px divided by h bar times our wave function psi of x comma t dx, where our psi here is exactly correspondent to this. So let's plug that in. This is going to give us phi of p comma t is going to equal, so let's move everything out. So first off, this constant at the front here, 1 divided by the square root of 2 pi h bar. And then we're going to move the constant here out as well, so multiplied by m omega divided by pi times h bar to the power of 1/4. Next off, the complex exponential, e to the negative I omega t divided by half. And then finally our integral in terms of x, so integral from negative infinity to infinity, starting with this middle term here, e to the negative m omega over 2h bar x squared, and then times e to the negative I px divided by h bar dx. Okay, so remember how exponentials multiply together. This can be combined ultimately into a single exponential to simplify this problem a little bit. So let's do that. This is going to simplify into the integral from negative infinity to infinity of e, and this is an integral in terms of x. So let's try, if we look at this, obviously, if we combine these two, we're going to get a polynomial. So let's try to set aside that polynomial and see what it gets. I'm going to factor out this negative m omega over 2h bar, so negative m omega over 2h bar at the start, and then I'm going to multiply by, let's see, so the first term just becomes x squared, the second term, the negative and the negative makes a positive. So this is going to be x, so p over h bar times 2h bar over m omega times x, right? So the h bars cancel, so we get 2p over m omega, and let's not forget the I almost forgot the I, so let's add the I here. So let's rewrite this. This is going to be 2p, or I guess 2ip divided by m omega, all multiplied by x. So this is going to be 2ip divided by m omega times x dx. And at this point, it's really up to you whether or not you want to just shove this into an integral calculator or not. I'm going to actually physically prove and solve this just to give us a little bit more of sort of a mathematical experience. or just a little bit of extra practice with doing integrals of this type. So if you want to just sort of plug this into an integral calculator and solve it that way, by all means, skip this next part, because I'm going to derive a relatively lengthy section of this next part of this video to solving this integral. So let's do that. Okay, so how do we solve this integral? Well, immediately, your first instinct when you look at this should be something along the lines of, hey, this is an exponential to the power of something, of sort of a variable to the second power. Or in this case, more generally, it's a variable that equates to a polynomial of power 2. So sort of the first instinct you should have when you have something like this is, hey, this looks kind of similar to sort of an ERF integral, right? Because an ERF integral, if we have an infinite integral of e to something like negative x squared, we can solve that by taking advantage of the property of the ERF function, right? And we can solve it that way. This integral, you technically do the exact same, but you have a little problem in that this lower term power with x, sort of, you need it to disappear. So how do we turn a polynomial into something that is just a variable squared? Well, immediately I think factorial, right? If I can complete the square and turn this into a factorial, into something that can be factored, then I can use u sub and basically just turn this into something that looks like e to the negative u squared. And from that point, I can just solve it via an ERF equivalent. So let's try that. So our goal is to turn this basically into something that we can square. So let's complete the square. This is going to be x squared plus 2ip over m omega times x. So if we want to complete the square, we take this b term that's in the middle here, and we halve it and square it. So we add ip over m omega squared. And if we do that, this is going to give us x plus ip over m omega factored, like that. So if we do that, right, then this integral is going to become an integral from negative infinity to infinity, e to the power of negative m omega over 2h bar. And if I want to add one of these, then I have to cancel it out with another exponential. So this is going to turn into e to the power of negative m omega over 2h bar multiplied by x squared plus 2ip divided by m omega plus, or I guess in this case minus, right? Let's see, p squared over m squared omega squared, because the I squared gives a negative. And I close this off, and to counteract that, I'm going to add another exponential with the opposite sign, so e to the power of negative m omega over 2h bar, and this time multiplied by positive p squared over m squared times omega squared. And I close this off with the dx. So, you know, this latter term on this side, this thing has no x dependency, so I can just move it out of our integral. And over here, I can simplify this by factoring it. So now this is going to give me e to the negative m omega over 2h bar times p squared m squared omega squared times the integral from negative infinity to positive infinity of e to the negative m omega over 2h bar. And I just realized that I added the e. That was my mistake. Do that again. This is just e to the power of that. So, whoops. Anyway, negative m omega over 2h bar, and I'm going to factor this term. So this is going to give me multiplied by x plus ip over m omega squared, and I close this off with a dx. So at this point, I can now use u sub. If I say, okay, u is going to equal x plus ip over m omega, and actually, you know what, just to make this even neater, let's try to turn that beginning term in front here also into part of the u. So let's say u is equal to the square root of m omega over 2h bar multiplied by x plus ip over m omega. And if I do this, well, in that case, du is going to equal the square root of m omega over 2h bar, and the x disappears, and that latter term is just a constant, so we just ignore it. And from that point, if I pull this back into this integral, then I'm going to get, so that front term, let's write it out in a slightly simpler way. This is going to be e to the power of, so this omega and this m cancels with the square terms, e to the power of negative p squared over 2h bar m omega times the integral from negative infinity to positive infinity, and then e to the power of negative u squared, right? And then, oh, whoops, I forgot to add the dx back here. So dx, in which case dx is now equal to square root of 2h bar over m omega times du. Go back to green. This is going to give me square root 2h bar over m omega times du. So at that point, now I just apply the concept of the ERF integral, right? Because I know that ERF of some variable z is going to equal 2 over the square root of pi times the integral from 0 to z of e to the negative t squared dt, right? So if that's the case, well, I know also that because of the fact that this is in terms of u squared, this is a symmetric integral, right? So this can be rewritten as 2 times e to the negative p squared over 2h bar m omega. And then I'm going to pull my 2h bar over m omega root out, integral, and now it's from 0 to infinity of e to the negative u squared du. So in that case, ERF of z times square root of pi divided by half is going to equal the integral from 0 to z e to the negative t squared dt. So in this case, our t is just u, and our z is going to be infinite, and ERF of infinity is just 1, so the integral from 0 to z, or in this case 0 to infinity, of e to the negative t squared dt is just going to equal the square root of pi over 2. So this is going to equal, well, the 2 at the front cancels, is going to be root pi e to the negative p squared over 2h bar m omega times the square root of 2h bar over m omega. And with that, we're ready to plug this in and solve the remainder of the problem. Okay, so now that we solved the integral, let's plug this in, as I've already done, and I've already simplified this. Our phi of p comma t is going to turn out to equal this expression. And remember what we care about, right? Because we've solved the first part of this problem, which is find the momentum space wave function. The second part is, what is the probability that a measurement of p is going to yield a value outside of the classical range? So remember, from sort of the classical or the statistical interpretation, right? If we want to find the probability of something, what we care about is not the wave function, but the magnitude squared of the wave function. So what we want is magnitude phi squared. So that's going to equal, well, if we magnitude phi square this, instantly our complex exponential disappears. This becomes 1 over m omega. This becomes the square root instead of a quarter root of m omega over pi h bar. And this is going to become, well, we just multiplied the top by 2, so e to the negative p squared over h bar m omega, like that. So now our question is, what is our dp interval, right? So we're trying to find the probability that a measurement of momentum yields something that is outside of the classical range. What is the classical range? Well, from, just standard normal classical mechanics, we know that the kinetic energy is equal to 1/2 mv squared. And, the kinetic energy is always going to be less than or equal to the total energy of our system, right? So in that case, if we rewrite this in terms of p, right? Because remember, we can rewrite kinetic energy in terms of momentum. This is actually equal to 1/2 p squared times 1 over m, right? And this is less than or equal to e. So p squared is less than or equal to 2me, or the magnitude of p is going to be less than or equal to the square root of 2me. This is our classical range for momentum. Basically, if you're looking at a system from a classical standpoint, its momentum is always going to be less than or equal to this value, where E is the energy of your actual system. So if we're trying to find the probability that something is outside of the classical range for momentum, then we're taking the integral of mag psi squared, or phi squared, and we're integrating from negative infinity to negative root 2me, and then from root 2me to positive infinity, right? So in that case, P is going to equal 2 over m omega from before, right? Or actually, you know what? I think I'm skipping a step. So let's go at this fundamentally. P is equal to 1 over m omega times the square root of m omega over pi h bar, and then multiplied by the integral from negative infinity to negative root 2me, e to the negative p squared over h bar m omega dp, plus the integral from root 2me to positive infinity, e to the negative p squared over h bar m omega dp. But here we know, because of the fact that this is in terms of p squared, right, we know that our magnitude phi squared term is going to be symmetrical about the y-axis. So what that tells us is that this integral is going to be the exact same as this integral. So there's nothing stopping us from just turning this into a single integral and just adding a factor of 2 at the front. This is going to be 2 over m omega times the square root of m omega over pi h bar times the integral root 2me to infinity of e to the negative p squared over h bar m omega dp. Okay, so at this point, what we do now is we recognize that, you know, we're dealing with the ground state of a simple harmonic oscillator, right? So in that case, well, we already know what the energy is, right? Because the ground state of a simple harmonic oscillator has just E is equal to h bar omega over 2. So if we plug that in, this is going to give us 2 over m omega square root m omega over pi h bar integral infinity at the top, at the bottom square root, let's see, 2m times h bar omega over 2, the 2's cancel, this is h bar m omega e to the power of negative p squared over h bar m omega dp. And at this point, as per the hint of this problem, right, look in the math table under normal distribution or error function for the numerical part, or just use Mathematica. So to make life easier for ourselves, we're just going to shove this into an integral calculator. It turns out that this integral specifically is going to give us about 0.16. So that is the probability of finding the momentum of a particle in the ground state simple harmonic oscillator with a momentum that is outside of our classical range. And with that, we are done with this problem.